Preparation of aldehydes and the ketones. Now we will discuss what are the different methods of preparing aldehydes and the ketones. Aldehydes and ketones can be prepared from the acid chlorides, right? Acid chlorides by two methods, two different reactions, right? Acid chloride, we know, suppose if you have RCOH, what is this we call it? We call it the carboxylic acid. And if you replace one of the hydroxide, if you replace here the hydroxide with the chlorine, what you will get? You get RCOCl. Now this is what you call as acid chloride, right? Acid chloride, this is an acid derivative, right? Acid chlorides, from these acid chlorides you can get aldehydes and the ketones. All right, from the acid chlorides here you can get aldehydes and ketones. You can react the acid chloride with the hydrogen in presence of a Lindblad catalyst, right? A Lindblad catalyst. And this is a very famous catalyst, and we use this Lindblad catalyst here to reduce this one. And here in this case, hydrogen will be replacing the chlorine, and you get a RCOH. So you get an aldehyde. All right, you get an aldehyde in this case. And we also actually add in this Lindblad catalyst, so we take a palladium and a barium sulfate and add some sulfur, right? That is important. This is what you call as a Lindblad catalyst. Okay, a very famous catalyst. Why we use this special catalyst? Why can't we use a simple palladium or a nickel here, right? The problem is that if you get an aldehyde, it may further be reduced if you use a simple palladium, or if you use a nickel or platinum, like that, because chances are that the double bond here in the aldehydes may be further reduced, and you will not get an aldehyde, you get something different. You may get alcohol from this one if you further reduce it. Correct. So if you want to stop the reaction here at the aldehydic stage, we use a Lindblad catalyst, right? We know the Lindblad catalysts do not act on the double bonds, whether you have a carbon-oxygen double bond or if you have a carbon-carbon double bond, right? So Lindblad catalyst is a very special catalyst. It doesn't act on a double bond, all right? So you can get aldehydes by the Rosenthal reaction. So this is what you call as a Rosenthal reaction. Acid chlorides react with the hydrogen gas in presence of a Lindblad catalyst. But see, in this reaction, you can only get aldehyde. You cannot get a ketone from the acid chlorides, right? Rosenthal reaction is used only to prepare aldehydes. If you want to get a ketone by the same source of a compound from this one, so you have to carry out a different reaction for that. You can see here in this example, you have a CH3CH2COCl, and you react with the hydrogen gas in presence of a Lindblad catalyst. Only this chlorine will be replaced by the hydrogen, so you get the CH3CH2COH and HCl. In this case, you can see here, we are again using the Lindblad catalyst. Sulfur is also there, right? Sulfur is very important one, because this sulfur actually poisons a little bit to this palladium. It decreases its activity. That's why it cannot further reduce the this double bond. And here in this case, you can replace the chlorine by the hydrogen. So what you get? You get a benzene ring attached with the C double bond OH. All right, and you get a HCl here. So this is our Rosenthal reduction. You can get both aldehyde, aliphatic and aromatic aldehydes. Now, if you want to get these aldehydes, if you want to get a ketone from the acid chlorides, so how you get it? You can get from acid chlorides, from the RCOCl, you can get a ketone also, but not reacting with the hydrogen gas. You have to use a different compound. Normally we use the dialkyl cadmiums here, right? Dialkyl cadmium is something that we normally use. This is our cadmium, and two alkyl groups attached to it, dialkyl cadmium. So what happens here in this case? One of the chlorine atom will be replaced by the alkyl group here. Okay, this is what you get, and this is again a substitution reaction. And what you get the RCOR in this case, and this both the alkyl groups actually, they can replace the two chlorine atoms in the two molecules. So you get two molecules of this, and you get a cadmium chloride, right? Cadmium chloride in this case. Here you can get a ketone, right? This is what you get, a ketone. But it's not a Rosenthal reduction. Rosenthal reduction is only reacting the acid chlorides with the hydrogen gas in presence of a Lindblad catalyst. And you can get a ketone also from the acid derivatives, from the acid chlorides, by using dialkyl cadmium. Here the alkyl actually replaces this chlorine from the acid derivative. So this is the reaction that we use to prepare ketones from the acid chlorides.